See, last class we talked about repairing of damaged buildings, including also restoration of damaged buildings to its near original state. And somewhere in that lecture, it said that repairing is not enough. If the structure is vulnerable, then we also need to do retrofitting to make it, to increase its resilience towards earthquake or cyclones. So that's what we're going to talk about today. What is retrofitting? It means to add or substitute parts or components to a structure to make it fit the changed context. And an example of that is, you are in a factory or a plant, and some equipment is changed. Equipment may be heavier or bigger. Then you don't necessarily demolish the support structure. You modify it. You modify it to accommodate either heavier or larger piece of equipment. That is retrofitting. Right? So the same way, if the building is not built to withstand a potentially destructive natural hazard like earthquake, cyclone, or flood, then it can be retrofitted. All right. Now just a glance at some of the past earthquakes. So this basically gives some numbers. You can see how large the numbers are in terms of houses getting demolished, houses getting damaged, number of deaths. And actually, I don't have a money figure here, but the money figure runs into hundreds of millions and billions. So all it says is that if you are not prepared for disaster, then the money which is really originally allocated for development planning, all that ends up in restoring, rehabilitating the people. All right. So basically, you don't want to be part of the statistics. And by having a proper disaster resilient home, you can make sure that you don't fall into these numbers. All right, now, you have seen some of these maps. I talked about this flood hazard map. Very small areas are really shown to be flood prone, but today things have changed. So, but anyway, these maps indicate where you are and what kind of hazard you have. So you can decide whether you're vulnerable or not. All right. Now, why opt for retrofitting instead of rebuilding? For vulnerability reduction, even for undamaged building. All right. Typically, after the disaster, there is a lot of talk of restoring back the damaged buildings. But in reality, rather than waiting for a disaster to happen, one can do what you call a pre-disaster earthquake, disaster risk reduction. Right? So even the undamaged building also needs to be retrofitted. Why? Now, reconstruction means first demolition, removal of debris, get new materials, and then reconstruction. Just like in repair also, I had mentioned the same thing, that if the structure is damaged and you are not going to restore it, that means you're going to demolish it and then rebuild it. So every stage costs money and time. So in retrofitting, essentially you're making small changes or adding some elements to only some components of the existing building. Alright? So rather than redoing the whole building, it's much faster than reconstructing. Now I'll give an example. We retrofitted a hospital in the town of Kupwara in Kashmir. And that particular hospital served a very large area. There was the only such hospital in that area. And typically the hospital will be just jam-packed until about 2 in the afternoon, because there's outpatient and there are visitors and all that. Now, if this hospital were to be demolished and rebuilt, it would easily take 5 years. Because demolition may not take time, but getting money to rebuild it would take time. Alright? So, and we were able to retrofit that within 2 months. So one can see the difference, and we did it while the hospital was functional. So it was not even that it will stop working. Alright, so it's much faster, but just one Mota number, 5 times cheaper. It costs about 20% of typically reconstruction of a disaster resilient building. And it means that all the conveniences created in the building are not lost. Just like what I said earlier, that if it was a hospital, of course, you have all kinds of things added into it. If it's a home, and I said that you construct a house, then you make it a home. You put in a lot of effort to make it a home. So if you're retrofitting, then whatever you have done, everything is not lost. Some of the things are lost and there to be redone. All right. Some more things. Retrofitting can be done in phases on portion of a building at a time. Okay, so it doesn't have to be done on the entire building at the same time, which means that the building use can be continued and the work can go on. So if you do it in phases, then certain portion is allocated to be retrofitted. Once that is over, you move over to the next phase. So that is the big advantage. It results in huge savings in national and global resources. Enormous amount of money. And much smaller carbon footprint than rebuilding. Alright, much smaller. So it's a greener option for reducing vulnerability. And this is the most important thing, that with the given money that you have, most number of people can be covered under the safety net. Okay, because it costs so little. Alright, now, so the most common approach has been to demolish damaged buildings and rebuild, because people like to work with a clean slate. I would, architect and engineer would rather say that, okay, just get rid of this, let's design it new and work with it. Alright? And they always find that retrofitting is a headache. So, but the question is, will there be enough resources to demolish all the vulnerable buildings? And the answer is no. So say no to reconstruction, and instead of that, will it not be better if the funds go longer ways? So say yes to retrofitting. Alright. Okay, this is just some of our work area. Maybe I shared a similar map earlier, but we started with Latu, and in between we went to Uttarakhand. There was an earthquake there. Then we went to Gujarat. There was an earthquake in 2000. Just few months before that big earthquake of 2001 in Kutch. And there was a talk, can there be more earthquakes? And that time I just told the reporter that yes, Kutch is so active, and actually, the last known earthquake at that point was almost 50 years ago. So, there is that cycle of about 50 years there. So the earthquake was overdue, and interestingly, it happened within 3 months after that. So Kutch is 2001 to 4. Then we worked in Kashmir, went there in 2006, 2007, 2008. Delhi, we did pre-disaster risk reduction on several schools of the Delhi Municipal Corporation. Then we did some work in UP, then again in Jammu. And then in Nepal, basically there was an earthquake in 2015. So 16, 17, 18, 20, 21. So basically, but our focus has been retrofitting, because we feel that that is the best option, and because also no one talks about it. So very interestingly, we are a small NGO, still we have done more work on masonry building retrofitting than anyone else in the country. It's an irony. So, basically we have worked on something like about 800 buildings in all different seismic zones. All right. Okay, now just a little bit about the earthquake scales. You have the magnitude scale. You must have heard of Richter scale, right? All the time, whenever there's an earthquake, you have the news, Richter scale, so on and so. It's essentially the magnitude of the energy released from the earthquake. All right? It doesn't have necessarily anything to do with the damage. And then you have intensity scale, which reflects the damage. So there are two scales. One is modified Mercalli scale. It estimates the shaking intensity from an earthquake at a specific location. Alright? The earthquake has happened somewhere at point A, We are talking about intensity at point B, okay, and we can be also talking about intensity at point C. Those will be completely different depending on how far the earthquake is and how the waves went up. But so specific location by considering its effect on people, objects, and buildings, right? How do people feel? What happens to different objects in the house? What kind of damage it causes. And then there is MSK scale. It's a macro seismic intensity scale used to evaluate the severity of ground shaking on the basis of observed effects in an area where earthquake transpires. Essentially, they do the same thing. Okay. So I think there's very little difference between them, but both the scales are used at different times. Right? Now, I have a description of the modified Mercalli scale, and it just says like intensity 6, then it is felt by all, many frightened, people run outdoors. Essentially, these are kind of observations of how people react, how people feel about it. Intensity 7, it's going to be a little bit more, and damage negligible to building with good design and construction, like to moderate damage in well-built and ordinary buildings, and so on and so forth. So you have levels going up to 9 and higher. All right. So like in seismic zone 5, what you get are the earthquake intensity 9 and 10 situation. All right. Now, also let's talk a little bit about the damage grade of masonry buildings. Earlier we had talked about damage category in the last lecture. There was this G1, G2, G3, G4, G5. That essentially is categorizing an individual damage. Now this particular wall may have several different cracks, and some cracks may be very fine, which would be like G1, but some cracks may be very wide, maybe G3, and part of that wall may be leaning, so that is G4 damage. But this is basically talking about the overall building. Okay. So grade 1 is negligible to slight damage. No structural damage is basically non-structural damage. There are also very little. Alright. Grade 2 is moderate damage, structural cracks in many walls. So this just describes, and ultimately, based on your observation, you will decide, what grade the damage is for that particular house. But this ultimately becomes very important because when you look at the overall picture, what percentage of buildings are in this particular grade, that dictates, how much, how severe the earthquake impact is and what kind of funds will be required to bring everything back to normal. All right. Then, another thing here, load-bearing masonry wall building types. Okay. This is the building types depending on what kind of walls the buildings have. All right. There is this building type A plus B, C plus D, and each one like a random double wall in mud mortar or without mortar. Sometimes it's called dry rubble masonry with sloping wooden roof falls in AA. Mud walls, adobe walls, 2 stories, also AB. So all this, very basic masonry walls and mud walls, they all fall in category A. Those are the most vulnerable buildings. Then we move a little bit higher. So you have, adobe walls of single story, not 2 stories. Rammed construction. Apparently these perform a little bit better. Then we go into category, the building type B. So semi-dressed rubble brought to pores with through stones and long cornerstones. I mentioned about in random rubble masonry, every 8.8 square meter, there is a stone which goes through and through the thickness of the wall. Basically, this works as a stitching of both the wall faces. Alright, this is the most critical element in any random rubble wall. So, this kind of building type B has the random rubble masonry with through stones and long cornerstones. The corner also will need long stones to connect one wall to the other. Alright. Also, the earthen walls, a lot of times you find the earthen walls have horizontal wooden elements. Very once in a while you find this. So these are definitely, in terms of earthquake, they perform better. So that in category B. Then you have B plus. So unreinforced brick masonry in mud mortar with vertical wood posts and horizontal timber elements. which are mentioned in IS 13828. So definitely that is better than what we had in category E. Then we move to C and C plus and D. D is the best with all the bands and vertical reinforcement and having the diagonals in the roofs and all that. So obviously, it will have the highest resistance to the disasters. All right. I mean, it's a little difficult to remember, but A to D, as we move into better and better quality building in terms of earthquake resilience. So now you have this table where the columns, starting from the top, you have seismic zone 2, seismic zone 3, seismic zone 4 and 5. So there is no seismic zone 1 now, all right? And in that, these are, MSK 6 or less. That is the amount of damage intensity. In zone 3, we have MSK 7, MSK 8, and then MSK 9 or more. Because that's the most likely earthquake that can happen in a foreseeable future in that particular seismic zone. Alright, so basically that we used to have seismic zone 1 to 5, but then 1 was eliminated some years back. So we have from 2, 3, 4, 5. So that's what it is. And then in each zone, what is the highest intensity earthquake that can happen? So in seismic zone 2, it is 6. Seismic zone 3, it is intensity 7 and 8 and 9. Alright. So then we look at these buildings. You have A plus, B plus, C plus, and D. So how they perform? So if you have a random rubble wall, without any bands or anything like that, in seismic zone 5, it will be mostly grade 5. Grade 5 is total collapse. Or, the rest will be grade 4. You come back to the lower zone, and even then you will have a few grade 5, and there's few houses, few is approximately 5% will be totally destroyed. Whereas, about 75% houses will have grade 4 damage, which means that, walls will have partially collapsed, walls may be out of plumb, walls may be burnt, and so on and so forth. So this actually gives an overall picture of what kind of damage a particular type of building can suffer in a particular zone. See, generally what happens is this, when after a disaster, when it's looking at the macro level picture, you have data from sensors that says that, what percentage of buildings are A, B, C, not so much in detail, but still there used to be fairly good sensors until recently. So based on that, you could project that in such and such location, if you have intensity MSK 8 earthquake, then what scenario will emerge and how many houses will be destroyed and so on and so forth. Okay? And that essentially also shows that, hey, there's a desperate need to retrofit and reduce that possible likely disaster. All right, now how to retrofit a building? We document the structure, just like earlier for damage. We document the structure, repair non-structural damage, identify the weaknesses, identify remedies, repair the structural damage G2, G3, G4. Right? Remember that? Grade 2 cracks, grade 3 cracks, then grade 4. Right? So before we do any retrofitting, all that structural damage has to be taken care of. We put back the box pretty much in the pre-disaster stage. Right? So whatever portions have collapsed, they have to be put back in order. Then, so that is the restored original state. Decide the sequence of retrofitting options and phasing. Based on the weaknesses, we have identified what retrofitting measures we will do. Now we decide the phasing. Whether we do. If it's a small house, sure, you can do the whole thing, start at the same time. But a large building, you will take it portion by portion, procure the materials, apply retrofitting measures, and finally you finish to match the original finish on the adjacent surfaces, so everything is hidden. Or we very much prefer to highlight the retrofitting measures. Like some of the pictures you may have seen, maybe you will see here. We want a message to be conveyed to people who visit that building that, hey, this is retrofitted. So sometimes some people will even write on top of that what it is, because you need to inspire people to retrofit that building. Now, okay, we have this building. Basically we have to get an idea of the complete idea of the state of the building that we're going to retrofit. So we need all the dimensions, we need the construction materials, structural elements, structural state of all parts. What stage is it in? Is it damaged, not damaged? Especially with reinforced concrete, you find a lot of times bars corroded, concrete spoiled, irrespective of the disaster or no disaster. So we have that fold down that we had seen earlier in the last class, right? Showing all that damage. That's exactly the same thing we have here. Now, just take a quick look at that at a glance. So you have a building with a pitch roof, and you have a variety of vulnerabilities. Okay, so I'm not going to read out all of them, but see here, actually, the W in green is wind, E is earthquake, F is flood. So vulnerabilities from all different natural phenomena are listed here. Okay, and simple thing like absence of connection between the floor and the walls. Right. So your floor here, you may have whatever slab, or you may have wooden floor joists and things like that, but they are not connected to the wall. That is one possible thing. Poor connection between the roof framing and the wall. Absence of tie at the eave projection, where you have this, eave, the roof is projecting out. In high wind area, you have to have some kind of a tie to prevent the roof from getting lifted up, roofing from getting lifted up. So a variety of things, weak anchoring of roofing to the gable wall and roof framing. All right. So basically, the items we had talked about earlier when we were talking about the disaster resistant masonry building. All right. So that's what it is. All right. So and if you have a reinforced concrete floor and the roof, then there are two, the issues with that pitch roof and the diagonal bracings and all that is not there. But then you have two issues here where you have a high masonry parapet with no ductility and no anchoring to the floor. Very common. We get these masonry walls all around in the terrace, which are like 2.5 feet, 3 feet high, right? And more often than not, they are just bricks laid on top of each other, and the wall is built, it's plastered and forgotten. And these break most easily. And also you have the reinforced concrete floor and the roof and the floor where there is no connection there. So these two are common in case of reinforced concrete slab. Otherwise, we have the full list in the other building. So first thing is identifying weakness in masonry construction. Now, typically, what we have done, especially after a disaster, when you go to an area and you do the study of the damage, that gives you a general trend that the buildings, there are stone buildings there, then it gives you an idea that, okay, these are the major weaknesses almost across the board. All right. So if there are brick masonry houses, certain type of weaknesses are there. So essentially, you study the damage as to what is happening. This classic thing. And you've seen that photograph earlier also. Basically, absence of wall-to-wall connection. And you see a few of these houses, it tells you that masons here don't know how to connect wall-to-wall. Right? And you can expect that this kind of weakness will be there in majority of houses. Right. This indicates that there is an absence of gable band and of connection between the roof and the gable wall, right? Because there was a gable wall here, right in this position. So this ridge beam, should have been connected to the gable band at the top. There should have been a gable band. So if that were there, this would not have happened. But the gable wall was there was no connection between that and the ridge beam. So the gable wall fell and down came the ridge beam and down came the roof. So it tells you, after seeing several buildings, what to expect, and based on that you prepare your action plan that these are going to be, the major weaknesses, and there'll be, the retrofitting features for each one of them. Some more examples: delamination, basically over interlocking in renderable wall between the two faces of wall. So this one happens, the inner faces remain, outer faces fallen down. So that means absence of through stones. Alright, you've seen this picture also earlier, and it clearly shows that the roof diaphragm doesn't exist. The roof doesn't have diagonal bracing, nor does it have connection with the gable wall. Alright, so then some damage like this would take place. This shows that the absence of bands. This kind of diagonal crack otherwise will not occur. I mean, if you have multiple bands, then there will be very limited crack will occur, and you will not have a full crack like that from bottom to top.
The lintel level.
Lintel and sill level. Yeah. Also, masonry columns, you see them everywhere. All right. It just says that, it's without reinforcement. Very common practice. So, this is some of the common types of weaknesses that we have. Now, if the earthquake is in this direction, these walls are going to be subjected to a lot of out-of-plane forces, and they will bend. All right. That wall and that wall will not have such deformation. It's going to go like that, and there will be very little deformation. Now, if you have the slab sitting on this roof, the slab is sitting on this wall and that wall, all the walls. So, slab, because those walls are not moving so much, it prevents the slab from moving. And that, when it is attached to this wall, it will also protect this wall. Alright? If the slab is only on these two walls and not on this wall, then the whole wall is going to go like that. Alright? So, having slab is providing a diaphragm. I mean, essentially, the shear force through the slab gets transmitted to both the walls and down to the ground. Now, instead of slab, if you had a roof with floor joists, timber joists, that whole thing will go like that, right? Am I right? Okay. So, in that you have diagonal bracings properly done, with struts and everything, and that will also pretty much act like the way the slab will do. And it will transfer the shear through those bracings and struts to the end wall. Right? So that's diaphragm. Okay. All right. Now, prescriptions of reducing vulnerability as per IS 1395. So if you have a random rubble wall, or if you have a thick brick wall, 14 inches or thicker, which can also delaminate, you have to cast in situ reinforced concrete bond elements. Correct? The stitching elements which will tie both the faces together. This is like I mentioned earlier. You have this cotton mattress with stitches every 6 inches, right? And if you don't have those stitches and you pick up a cotton mattress, what will happen? Right? All that cotton will come down and the fabric will go like that. So that basically happens in thick walls. Okay, there's no stitching done, then you got problems. All right. Then install seismic belt at floor level, eave level, and in gable walls. Right. So you will have at this level, all these levels you will have, and also if there is a gable masonry wall, then the belt will also go on that. Then install vertical reinforcement in each corner and anchor roof with it. So the reinforcement, the vertical belt will go from bottom all the way up from the foundation to the top of the wall, and the roof will be anchored to, roof elements will be anchored to it. Install encasement around the openings. You remember the tearing of that paper, the tape prevents, so encasing the openings. If these openings do not have encasing all around with 2 bars, then you need to provide that. Install struts and bracings in timber-lace wall. I mean, if you have a timber-lace wall like what we have here, and if it doesn't have proper bracing around them, then you would also do that. Then install collar beams across principal rafters and diagonal bracings in the roof. Collar beams are these, okay, between the two rafters opposite. You see it? I mean, these collar, what does collar beam do? They reduce the lateral thrust on the walls and anchor roof trusses to walls with MS brackets. Okay, whatever roof elements you have, they have to be anchored down by some means. Okay, it can be mild steel brackets, can be simple rods, can be wires, variety of it. All right. Okay, and install struts and bracings above the attic floor. So if you have the attic floor which is made of timber, or it can be even made of angles and stone. Okay, because that's also a very common thing that is done in many places where you have little girders or channels or something and stone is placed. So that will also have the same problem. They will have to provide the diagonals and the struts. All right. So anyway, this is basically the same list. And so first of all, we have to start with deciding which category the building is B, C, D, and E from table 2, page 7 on IS 13935. All right. So we'll come to that. Now, so you had the same drawing, the fold out with that damage already repaired. Now we are adding the retrofitting elements. All right, the lintel level C-steel belt is also added in the plan. You have sill level C-steel belt. You have cast in C2 stitching elements, right? You see that? Here are the cast in C2. Vertical corner ferrocement straps, vertical reinforcement on both faces. And what else? Okay. Right, now this is a typical plan that is to be drawn, and the plan shows all the elements which are to be added. You can use any kind of notations, and you need a legend for that. But like this wavy line is a belt, seismic belt. This blue are the encasement around the opening. Right, there is a window here. So there is encasement on both sides, encasement here. Now, this particular room it's a long wall, and the wall length is more than 8 meters, so it requires buttress, to prevent too much of deflection. So instead of buttress, what we have added are the vertical seismic straps here. The ferrocement straps are put in from foundation all the way to the roof bottom. Okay. So anyway, so basically you see all the elements are shown in this. Actually, in the right side picture, you get an idea of that wall. The plaster is removed for installing the lintel level belt. Here the plaster is removed on both sides of the doors for installing the encasement. Also, you see some of this. This is the cast in C2 stitching elements. So this is the gable wall. You can see, get an idea of the various belts. Now again, in this, oftentimes you have to compromise. Like here, you would have liked to take the belt all the way to the top, make a proper triangle, but this place was not accessible. There was that was totally closed. It was not possible to get in there. So we said, okay, then we'll keep the belt below that. All right. So something better than nothing. Okay, you can't have the best, but these have that. All right. Now, first is the stitching elements against bulging and delamination. You remember I talked about bulging, where a portion of the face bulges out. Okay. So that is this separation is started. And as we said, it's in the state of impending collapse. So some more shaking, and that bulge portion, the face may collapse. All right. So that is then it's called delamination. If one face falls, and is delamination. So what is required is to make holes. Make holes at one for every 0.8 square meter or 8 square feet. Right? And this is a very delicate operation. So ideally, the hole has to be like a dumbbell shape. So as you see here, it's bigger near the faces and narrow in the middle. And then you clean it out, all the dust and everything. And then you put a little bit of concrete, fill up the bottom, put this rod, 8 mm deformed bar on concrete, and then you fill up the whole thing. Okay, and this actually hole making is a very delicate operation. And one other thing is you don't use a crowbar. You've seen people doing that, and then also some of the first retrofitting that was done in Latur, Professor Arya had left instructions with the irrigation department engineers. Okay, so they retrofitted a house, and we visited the house after it was retrofitted. Also, I think it was a little bit during also. And these holes should not be bigger than that, about 6 to 8 inches diameter. But what these guys started doing, they started making holes, and then they would remove this stone and that stone, and ultimately the holes started becoming this big. And whatever people saw, they said, hell no, we don't want to retrofit that house. It was a scary scenario, and all of a sudden you see this wall with huge holes all across. So, then I went to Roorkee, met Professor Arya, I said, this is what happened. How can that happen? We don't do it like that. So, basically we learned, we understood what was to be done, and then, and very interesting is the first house we retrofitted in Latur, the house owner came and made the holes. He's a farmer, he's used to physical work, and it's his house. I mean, he had practically abandoned the house, and we also wanted a house which was abandoned, so if something happens, then we don't get into trouble. Now, alright, basically the way we figured out was that we decide first where things are to be done, we mark these places, if there's any kind of plaster, we remove it, and then we select the stone which is not very big, because stones vary in sizes. You can go 6 inches here, 6 inches here, it doesn't matter. And then we select the stone, and we got these rods made, alright, with pointed end. So with that we would start removing the mortar from all around, alright. And then once that is clean, you start prying it, you do a little bit this way, that way. Slowly the stone becomes loose, you remove it. And you make sure that by doing that, you'll have always some stones here or there. If you start pulling all that, then the hole gets bigger. And then once the one stone is removed from the face, then with the same rod, we would dig in through that inner muck and go to the other side. It'll start hitting a stone. You'll have somebody standing on the other side, and they'll say, okay, this looks like a stone. And then you do the same process, and by and large it works. But it is done in a very delicate manner. And also basically the construction in Latur and construction in Uttarakhand, although random double masonry, mud mortar, stones are of completely different type. Latur was basalt, very different. Uttarakhand has different stones which are flat. So removal of stone, the whole process changes. And when we went to Uttarakhand for the first time, Rupal, myself, a couple of engineers, we went and ourselves worked on one wall which was part of a ruin. Just to understand that how to remove the stone. So it's not something extremely difficult, but you have to do it so that you don't damage it. So alright, and basically once this is filled, it's cured, right, properly. And this we have done testing on it, and it works beautifully. Our shock table test showed that this was very, very effective. Alright. Different types of stone require different ways of making holes. Exercise extreme square and don't damage. Alright. Number 2. So it's clear about the stitching elements. About the belt. So it's an uninterrupted seismic belt of ferrocement are to be installed at various levels. Right? And actually Rupal has brought this box to show. But this is our box type construction. Right? Essentially, You put a belt like this around, and it's important that this is properly anchored to it. Okay, so anyway, is basically a pretty straightforward thing. You have to decide the alignment of the belt, and you have to prepare the surface of the belt so that you are able to properly anchor it. Alright, anchoring requires certain connectors in the wall. It also uses nails. Some connectors are through and through. You also have to make once again some holes in the wall and put your connectors in it. And these are L-shaped rods, which will be connected, with which the belt is connected. And belt essentially consists of weld wire mesh. It can be 10 gauge, 13 gauge. The code specifies exactly how many wires and what gauge. And if you get thinner gauge, then you can add reinforcing rods to it. You calculate the steel area. But see, connection to the wall is important. I always talk about the belt. This has its loops. But if it didn't have the loops, and you start moving, your belt and your pant are going to separate. And you got a problem. So same thing is having proper connection. Then only the belt comes into action. Alright. Okay, one more thing is that anytime there is any kind of ferrocement to be connected to the wall, there should always be half an inch gap, 12 millimeter gap between the weld mesh and the wall surface. So that when the plaster is applied, there is a layer of plaster that goes between the wall and the weld mesh, and the second layer is outside. You don't want weld mesh sticking to the wall, because if there is ever any separation, the water will enter and your mesh will be corroded in no time. So the mesh has to be fully encased in 1:3 model. Alright? There is an L-shaped connector. Just like we made the holes for stitching element, in that there was a rod with double hooks only. This will have one hook and an L-shaped rod that comes out. So it is really very secure inside, and the belt wire mesh is connected to that. You can see the this leg of the L-shaped rod. Alright. So the wire mesh. As you can see along the just under the gable wall. Alright, there is an extra belt put in right here at this higher level. Also, we have been using some tie rods also. A lot of times the walls are very long, then the belt itself is also too long. So, although the code doesn't say anything about tie rod, we have been using it, and I think it's a good practice. Alright. Okay, then comes to openings. So encasing of opening, basically using, once again, the weld wire mesh, ferrocement, right? And then this is connected, if there is any chaja on the top, then it has to be connected with proper dowels there. Now sometimes there are a lot of excessive openings as per the code, then you end up closing also. Here's a window that has been closed off. Right? So you have to go by what the code describes and prescribes quite exactly, and you stick to that. And there's an easier way to do it, just filling up openings. This is just pictorial sequence of how the belt is installed. You start laying out the alignment with a cutter. The plaster is, you start cutting, removing the plaster, so on and so forth. I won't go into detail, but in general, this was it's from a school in Delhi, Municipal Corporation. And now this is the belt making. So here the belt, you can see the weld wire mesh bundles, they are opened up, and then as per the specifications, the belts are cut, and if required, then reinforcement is added to it. As you can see here the 6 mm bars are added to it, and then once the whole thing is ready, the wall surface is also ready. So 3 or 4 individuals will pick it up and anchor it on the wall. So here are some more examples. Okay, so you have vertical and horizontal. Those connections have to be there properly with proper overlap. And in brick, the nails work beautifully. Then you don't need any other shear connectors. So with random rubble, always there is more trouble. Alright, the vertical code talks about vertical bars and also gives an option of ferrocement. So either way, this is done. And the gable belt is connected to the vertical element, and if it's possible, then the roof joists are also, roof purlins are connected to these belts. Instead of the ferrocement, you are using a single rod and proper. Once again, in this you have a shear connector put in, and that you do concreting of that, so you have all the shear connectors in proper position, and then the rod is connected, and then it is encased. So here the rod is about 35 to 40 millimeters away from both the walls, so that you have proper concreting going all around the vertical rod. Alright. Yeah, this few examples. And if you have double story or 3-story building, then you will have rods going right through the wall. So you'll have to drill this in the slab, and they can go right through. Yeah, anyway, these are already covered. You can read later on, but otherwise, basically it talks about all the proper encasement and proper anchoring, preparing the surface. Alright. Now, just a simple details. If you have 2 stories, then this rod goes straight through the slab. The hole is grouted, and then it connects with the reinforcement in the roof slab. Sometimes the wall thicknesses may change, then you have to just change the alignment. Alright. Okay, now it comes to the roof anchors. So whatever rafters you have, they can be connected with with high gauge galvanized iron wires before coming from the belt. You can see something like this. Yeah, here's the detail of the rod that I mentioned. That you have proper overlap with the bars, and then this concreting is done. Now, diagonal bracings in the roof. Now, this kind of roof, one can use timber bracings, diagonals, and they can be attached with proper gusset plates and all. Where it is possible to do all this drilling and cutting and all that, one can go with this. Then even the bracings can be nailed to the rafters wherever possible, so gives better connection with the roof elements. Alright, so instead of that, in really deep rural areas, rather than going with timber braces and gusset plate and all that, we have been using galvanized iron wires, 3, 4, 5 wires together, and they're properly stretched and then twisted. So twisting then gives good pre-tensioning to it. So variety of ways it can be done, but you have to properly, you have to make the proper configuration of how it will be putting from where to where they will go. You have to see the stress path, how the forces will go. Also, too much of twisting can break the wires. Okay, so one has to be careful not to go over there. Now, miscellaneous items. Yeah, one of the things, if you have angle of tiles, then with this kind of contraption, they can be anchored down. This is in an earthquake, too much of shaking results into falling off of tiles. In case of cyclone also, it's even a bigger problem. So, timber columns, this is from Latour. You have proper knee braces, and if you have a masonry column, then you can put properly encased in bars all around rings. And then on the top, if you have timber element like this, then these bars can go over that, and they have to be nailed down properly. Right? So something like this, of course, but this is a lot of effort, and one has to be very careful, because if the column is done in mud mortar, then it is extremely precarious. So a situation like that, it may be worthwhile removing, dismantling the column, and just using, reusing the same bricks and bring it up with a bar in the middle. Alright, so there is, we have IS 1395-2009, Bureau of Indian Standard guidelines, which are very, very useful. And these are some of the publications that we have made for different agencies, government agencies or international agencies. There was a retrofitting manual we made for Kashmir. There was one for Himachal Pradesh and Uttarakhand. Recently we made one for Nepal. So, yeah. These are available, PDF. On our website we have PDF files of these manuals. If anyone wants to look at them. We also have a few copies. So anyway, you can show them later. Let me quickly move on. Actually, assess the need for repair is done and okay. Evolve solutions, because there is no textbook situation. Look at each building element and then structure as a whole. How it's going to be. Right? Be ready for real life situation. Once we had a problem, we anticipated that there'll be a lintel band, and then we started doing work and the removed plaster and there was no lintel band. Or sometimes you expect that there is no lintel band, and then when you open it up, you will find it. You will find it on some walls, you will find it missing. So, we are working with an existing building, you have to be very, very careful about properly documenting and studying the building. Okay. Right procedures. As I mentioned earlier, use skill and trick and not brute strength. The retrofitting scenario is not very good in India. People are, unfortunately, most of these agencies, is the health department or state government, they would rather demolish the building and rebuild it. So as and when they will have funds, they will do it. They will wait for future rather than retrofitting right now. Engineers find it as too complicated, and in Latur, the whole engineering establishment, this was basically Professor Agya's idea, and the whole engineering establishment, from chief engineer to whatever 600 engineers we had, nobody believed in it. And Arya had to do a shock table test specifically to show that, retrofitting does work. So that's the problem here. So, and we have seen buildings are either abandoned and something new is built in Gujarat in one block. One of the non-profit agencies with a lot of money, well-meaning, but they abandoned all the schools and they rebuilt the schools. Enormous amount of money wasted. Engineers lack confidence. And people do not readily accept retrofitting, but we have seen that if you have proper logic, if you we have been able to convince a lot of people to do it. Anyway, easier to start with clean slate. Prefer to demolish and go for new RC buildings. Engineers like that. Also, a lot of times there is that, there is a hidden agenda that somebody wants to make money. In Uttarakhand, it was very interesting. We had Sarva Shiksha Abhiyan, there was a government education department program. And all the engineers who were there, they were also contractors. So they would rather demolish that building and get a contract on the side, maybe under somebody else's name, and do it, rather than worry about all this retrofitting. So, that's the ground realities. Alright, anyway, so make saving of building as a priority, not reconstructing. Be satisfied with better if the best is not attainable. Best is always the enemy of better. We too, when we go to a building, we go with this mind that no, we're not going to demolish it. You go with that mindset, then you figure out the way. Go for incremental approach. Funds are not enough. That is the great advantage that retrofitting has. For given resources, retrofitting, we go. Alright, anyway. So, that's about it.